அதே மாதிரி ஃபேன் அங்கே இருக்கு நவர்றா
A very good morning, every one of you. We warm welcome for the third day FDP and data science emerging technology in data science. So it's my great pleasure to invite Mr. Shivasankar, Dr. Shivasankar Sukumar from IIT Gandhinagar is going to deliver the session today. The topic name is predictive models and machine learning workflow for automation. Okay, I welcome sir. I welcome you, sir. Now I'll ask Sukumar sir to take over the session.
Thank you, Mr. Neelakandan. So, welcome everyone. So, whoever attends my session, thanks for joining my session. I'm Dr. Shivasankar. I'm working at IIT Gandhinagar as a postdoctoral research fellow. My background, I'm an electrical engineer. My bachelor's and my master's and my PhD is all in electrical engineering, specialized in energy and power systems. So I'm an electrical power system engineer. So, but I have a great interest towards data science and data engineering. So today I'll share uh, hands-on experience, like how to work on with the topic of data science and data analytics, and how to work on with developing, building a machine learning model. So that I'll be doing it today. I'll be showing a hands-on. I'll be sharing you hands-on session. So so let's join it. So I'll be sharing my screen so that it will be visible to you. I hope my screen is visible. I hope the my screen is visible. I'll just increase the volume. I hope everyone can see my screen, right? Okay. So this is the Jupyter notebook. What I'm working on, what I work on for power system and energy related problem. Most of the problems what I work on is relevant to electrical engineering. Uh, Currently, I'm working on for a project called the Encoder, which is uh, automation of smart city, automation of some important infrastructures in smart city using machine learning algorithms. So, hello. So, audio கேக்குதா? Most of the problems what I work on is mostly on forecasting algorithms and predictions. Most of the algorithms what I work on is forecasting and predictions algorithm. So mostly I work on like currently I work on like deep learning LSTM models for forecasting solar PV output power. But here for this today's session, I will not be taking an electrical or electrical problem. I'll be taking a general data set. So the general data set, I will show you how to clean the data set, how to before building a model, how to clean the data set, how to work on the data set, and what are the features, feature analysis, feature extraction, and feature engineering. And later on, after finishing these steps, I'll be showing you how to choose a machine learning model to train the data set, and the trained model, how to save it as a machine learning trained file in your local disk, and the local disk can be and the trained model can be fetched anytime and can be used for predicting the data set what you have for the future, for predicting the future. So I'll be showing you. So actually, it is an enormous like flow of code. So as a result, I have already like put on the codes and analysis. I'll brief each and every steps. So I have worked on this is sample data set. So before going into the code, I would like to show you the data set in CSV file format. So this is the the problem what I've taken is predicting the sale price of house, predicting the sale price of house with different features. So basically the sale price of house in dollars. So you have to predict the sale price of house based on the features provided by features considered. So this problem, like you have to predict a numeric value. So this problem uh, is a regression problem. So this is a regression problem. You are going to predict the sale price of house in dollars, which is a numeric value based on the features what I'm just showing it to you. So here you can see two files. So you'll be able to see two files, the test file and the train file. So this is the test file. What I'm showing to you is the train file. So the test file is on the right hand side. So now this is the trained file. So in this trained file, these are like if you see the size of this trained file, if you see the size of the trained file, you can see that it is like an if you see the size of the trained file, you can see it is the count comes to 81. So totally there are 81 features, and this in this training file, this the last column is the sale price column, which you will be this one is the predictor variable, which will be used for training these features. So out of 81 column features, so the last feature, sale price, is the predictor feature, and the first the features what we are going to plot, like what we are going to use it to train against this predictor feature called sale price. So if you see, these are the feature names. Uh, so MS zoning, lot footage in square feet, area, lot area, and the street type street. So this is the data sets. So when you look into this data set, so when you look into this data set, there are a lot of before going into jumping into the machine learning models, please look into the data set. There are like a lot of some features have numeric variables like lot foot frontage and MS class subclass have or like and the lot area. These are numeric variables, but the most of the variables are not a numeric variable. These are like some many are categorical variables where these are based on the categories they have split. So when you load this file in Python, so the data type, the Python will understand these numeric variables as float, mostly as float, and these categorials, these as alphabetical variables will be understood as objects. So the data type in Python, it will be taking it as objects. So these are the these are the features what I'm going to use it. So now this is about the training file. Now coming to the testing file, if you see the testing, these are the testing, this is the testing file. If you see the testing file, the number of columns, if you see the number of columns count is showing as 80. So it is not 81. So meaning you have to predict the sale price of these particular features. I have for these particular features you have to predict the sale price of that house. So that we have to work on. So this one is the completed testing file which has only 80 features, and this is the training file which have 81 features. The last column feature, that is the sale price feature, is the predictor variable what we needs to predict, and these are the features what we have to train against these predictors. So let us now jump to the code. Now coming to this code, I'm using pandas library. I'm using pandas library to uh, I'm using pandas library to to fetch the values of this to fetch the CSV files, train and testing CSV file. So let me first run this. So in this cell, I'll be fetching the data at training and testing data from both the CSV file, and I'll be saving it as a data frame. And if you see, when I run this, if you see the shape of this data frame, meaning the the training data frame. So when you see the shape, the number of columns and number of row features for this training CSV file, you see it has like 1,460 rows and 81 columns. And if you see the shape of the test data frame, test underscore data frame, you, the number of row features is 1,459 and 80 column features. So this is the training file. The training data frame has 81 column features, but the testing data frame has 80 column features. The training has the predictor feature also, that is the sale price feature. So testing data frame does not have that sale price which we need to predict it. So mostly this testing data frame, meaning that the testing data frame will be using against the trained model, meaning first we will use the training data frame only to build the entire model. So the feature extractions, feature engineering, feature scaling, all these procedures will be taken. All these procedures will be done to the both these data frames, and you'll use the important features from the training data frame only to build a model, and you save that model in your local disk, and against the trained model you'll be using that test data frame to predict the value. So this data frame will be used only against the test, will be used only against the trained machine learning model, not for this will not be used for training. This will be, and the training data will be used only for training the model, train or building the machine learning algorithm. So here what I do is, actually if you see the data set, there is one feature called ID. So this ID is 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 incremental numbers 1, 2, 3. It is an ID. So that feature may not be needed. So that is of no importance. So I just removed, I'm just dropping it from both the training and the testing data set. So I have just removed it. So after I remove the ID, so you can see the shape of the training and the testing data set. 81, after 81 was the original shape. 81 is the column feature, original column feature. And now after removing the ID, the column feature for training set is 80. And the same as 80 becomes the 79 for testing features. So before going into the model, this is the basic information of that training data set. So you can use the describe actually training data. This is the data frame. Train underscore data is the data frame having the training file. So this one is basic information of these features. So what are how many number of row features are, how many number of rows is available, how many values is available, how many non values are available, what is the data type. So all these details will be there if you go with the .info. Suppose if you are going with the, if you want to describe, so describe is for each and every features, it will tell you what is the mean standard deviation, what is the minimum, what is the maximum. So you can just from describe, you can just see how each of the feature is being distributed among the data sets. One feature may be equally distributed, a normal distribution will be there, and some other feature, a normal distribution will not be there. Mostly it will be skewed distribution will be there. Whether it will be positive skewedness will be there, sometimes negative skewedness will be there. Uh, so those types of insight you can get it from the data, and more visualization, more visualized view you can also plot it. So I'll be using the plot to show how sweet the data stage. So now this is the basic information. What is the mean of that particular feature? What is the median? What is the standard deviation? How the data is distributed, like minimum, maximum, 25% and 50% and 75%. How the distribution varies. So if you see the variation of the lot footage alone, minimum is 21. At 25% it is 59. At 50% it is 69. So and at 75% it is 80. So from minimum to 75% it is like quite well distributed. But from 75% from 8 to the maximum it jumps 80 to 313. So there is a huge variation in the data set. So mostly this type of data distribution will go for positive squeedness. So that is maybe few outliers are available in the data set, so which we need to identify. So I'll tell you how to do that. So before going into those procedures, this is the usefulness for describe, using the describe function. If you wanted to go for info will give you the idea what type of data set, what type of data type, and how many null values, how many non-null values are available. So those informations against each and every feature, you can get that information. So if you see the data, type, in float is all the numeric, object is all alphabetical data types, where like REG, LBL, all pop. So inside, so these are alphabetical, and which is categorized as objects, in this data type. So you could see this data type is not completely numeric. So this has mix of both the numeric and also alphabetical data types. So which is also another concern. We have to convert, before training a model, we have to convert all the data types into a numeric, So it should be a uniform data set before we go to building a machine learning model. So we have to change these data types also. So now before going it, we just go for another some deep analysis. So I just wanted to check how many percentage, how much for each and against each and every feature. I want to check how many null values are there. So I just use the is null function. I just use to is null function. Actually, is null function, whether it is null function will return either true or false. If a column feature has if a column feature does not have any null value, then that is null function will return false. If the column feature at least have one single null value or NaN or missing values, this is null function will return true. So I'm using this is null function against each and every feature, actually against this data frame, and I am going to I am going to take the sum of all the null values against each and every features. So I'm just going to run it. So now, so until this part of code, I just calculated the total number of null values and the percentage of missing null values. So if you, I marked I put it in this portion, like I printed it here. If you see, pool QC feature has 1453 null values. So this gives the total count of null values for against this feature, which is the total column. The total row numbers is 1460. Out of 1460, this feature, out of 1460, 1453 has null values, which is like 99% of 99.5%. Like, so these are for each and every features. If you see roof style has zero null values, which is 0%. So these are the count percentage of count for null values. Usually, it is good to have the null values removed from the data set. So if the null values are too much, it is better to remove the entire feature. If the null values are less, like meaning less than 15%, actually some standard I follow with me, like I'll check for each and every feature, and for each and every feature I calculate how much percentage of null values are present against the feature, and if it is more than like 15 or 16%, I'll remove the feature. I'll not use the feature. If it is less than 15 or 16%, I'll keep it and I'll replace the null values against some dummy variables or some like forward fill method, backward fill methods are there. I'll fill up those null values. So here I identify how many percentage of null values are present against each and every feature, and you can see that more than 15%. It's 1, 2, 3, 4, 5, 6. So these six features has null values more than 15%. So it is a very good thing to eliminate or like remove these column features. So it is very good to remove these column features from the data set. So now I have removed this column feature using a simple formula. So I remove these column features which has more than 16%. So which has more than 16%, I remove these column features. And after removing these column features, like I am just printing the shape. I'm just printing the shape of training and the testing data frames. So 1, 2, 3, 4, 5, 6. So 6 features I have removed from the training and also from the testing. So once remove it from the training, and also I am also removing it from the testing. So the original column features, we before removing it was 80. So I removed 6 from it. So you'll get 74 here, 73. So that is what we got it. It is 74 and 73, right? So I am removing it. So now I'm just checking how many number of total values are there in the training data set alone, meaning the trained data. So when I just run it, so these are the total number of so these are like the 81, 81, 81. So these are the remaining missing numbers which are there. So now for these features, I'm keeping it with my data set because it has only 5%, like 5.5%. So it is better to keep it, not to remove that feature. So I'm filling those 81 data points are remain these data points with automatic fill NA method. Like I'm using forward fill method to fill the null values. So I just fill it with the so this fill NA method will identify the null features which have NaN or null. So those values will be filled automatically. So forward fill is you copy meaning at the index 1 there is some value, index 2 is a missing value. Forward fill will copy and replace the index 2 with the same number as index 1. So that is the forward fill method. So I use forward fill. So now after I have used the forward fill. So I print the number of null values. So here the number of null values is 0. So for this I applied for both the testing and also the training data frame. So as of now, there is no null features in my data set as of now. So now coming to feature conversion. So in the data set, I have showed you that my feature is combined mix of both, which has numeric and also alphabetic. So I need to convert it. So the alphabetic variables will be identified as data type in as object in Python. So I'm categorizing it. I'm categorizing it how many column features and how many numerical features are there. So in my data set, in my trained data frame, I have total of 74 features, I said. So out of 74, 38 are categorical variables and 36 are numerical variables. So now my objective is I have to convert all these categorical variables into a numerical variables. So which is an important step we have to follow. We cannot build a regression model having mix of both the numerical and categorical variables. We have to make the data set complete numeric variables, so that from these numeric variables in these features, the regression problem of the predicting the sale price of the house is carried out, can be done. So we here in this step we have identified how many categorical variables are there. We need to convert it into we need to convert these 38 categorical variables into numerical variables. So we have to take. So this is just an example, like this is just an example of what are these numerical, numerical variables are there available in the training data set. So here, what are the categorical variables that are available in the training data set? These are categorical variables. So all these categorical variables I need to convert into equivalent numbers. So for how do you convert? There are like one or two steps. The prominent step of what I use is I use a label encoder method. So I use label encoder method to convert all the categorical variables in both the testing and in the training data set to convert it into a equivalent numerical variable. So I convert it. I convert all the categorical variables. I convert all the categorical variables into a numerical features in both the testing and training data set. So here the number of features for training is like 74 and number of features for testing is 73. 73, why 73? Because we don't have sale price feature in that testing data frame, which we need to do it. So we don't have it. So now, after I run it, so you can see the head will give you the header top five values of the entire feature. So now the head of the now you can see uh, when I just open the data. Okay, now street or like MS zoning, MS RL RM. So C. So like lot of these categorical variables are there. So MS zoning has converted, meaning it has converted these categorical variables into equivalent to numerical variables. So it will convert. It will take RL as 3, RM as 2, C as 1. It will do for the entire column feature. So this procedure will be done for all the categorical variables present in the training data frame, which is street, land condition, utilities, lot configuration. So all these is done. So this is the converted. This is the converted categorical into numerical variable, which is present, which I'm showing it to you. So this is, I have done this conversion for both the testing and also for the training data frame. Previously I showed it for the training data frame. Now I'm showing it for the testing data frame. So now I'm showing it for the testing data frame. So this testing data frame does not have sale price feature. Sale price feature, we need to predict it. That should be the outcome of the machine learning algorithm. So now we have the entire data set, all the data sets. So until now, the steps what we had followed is, what we had followed is, we have the data set. For all the data sets, first step, we try to calculate the numbers. First, we try to calculate, is there any missing numbers? And we identify the missing numbers, and we drop the column feature which has more percentage of missing values, and we like forward filling. We use the forward filling method to fill the missing values or NAM, which has less percentage of uh, missing numbers. So and the second step, we identified how many number of categorical and numerical variables are there, and its conversion. Now the entire data set what we have now is completely numerical variables. Now we have to do correlation analysis. Why we wanted to do correlation analysis is, there are 70 as of now. If you go to if you see the training data set, there are 74. For training data set, there are 74 columns, meaning 74 column features. So, is it possible to train all the 74 data set, all the 74 column features to build a machine learning model to contribute a regression to solve to predict the sale price of the house? No, actually, practically it is not possible. So only few of these 74 column features will really contribute for solving for calculating or will contribute. So we have to identify what are those features. So and one more difficulty is we cannot use all the 74 features in training the machine learning models because we need 74 inputs, and training the machine learning models with the enormous input will take too much training time. So like lot of difficult practical difficulties are there. So we cannot go with all 74. So correlation analysis will help you to identify what are the or relevant features relevant to the sale price of the house, or in, of more importance, which can be fetched and it can be used for the future for building the machine learning models to predict or forecast the sale price of the house. So we need to identify that. For that, we use correlation analysis. So correlation analysis, I have these. This correlation analysis is done, and out of this, like top 15 to 20 features can be extracted based on the correlation values. Usually, correlation analysis will give values between -1 to 1. How do we interpret the results is if the values is closer to 1, then any positive correlation, that is a positive correlation. Any correlation which has a negative value is a negative correlation. And if it is a positive and very closer to 1, it has a strong positive correlation, which is a very good sign. And if features have uh, like negative values and negative close to 1, negative values, those features have some negative relationship, meaning positive correlation. When you increase the value of x, the value of y will also increase. But in the negative correlation, when you increase the x, y will decrease. In some machine learning, like in some, for some problem, negative correlation may also be necessary, but for us, it is not needed. So I'm not using a negative correlation. And for some correlations, for some features, the correlation value may show closer to 0, which shows it is not at all correlated. So it is completely irrelevant. So from the correlation analysis, what I'm doing is I compare. I said totally 74 features are there. Out of 74 features, 73 features I have to use to predict the 74th feature, that is the sale price. Now, I compare what is the relationship, how strong is the relationship between the sale price and for each and every feature for all the 73 features through some numerical measure. That is what the correlation analysis is. So now this is the heat map, what I show in visualizing the correlation analysis. So the green ones are like a good correlation. So this heat map may not be visible. So what I've done is I have taken the top 15 features which are highly correlated with the sale price of the house. So I'm just showing you with the smaller heat map. So if you see this second heat map, the overall quality, ground living area, garage cars, garage area, total basement in square feet, first floor square feet. So these are some features which have positive relationship with the sale price, meaning if all these values increase, it also have a positive impact, like there will be an increase in sale price. If all these features values decrease, there will be decrease in sale price. So it is positively correlated. So the relationship between the sale price and the relationship between the sale price and each and every feature is shown in this diagram, in this heat map figure. So in case of numbers, how much percentage it is relevant. So how much percentage it is relevant? For example, sale price and overall quality, these two variables are like 80% correlated, like 0.79% correlated, and the sale price and the ground living area, the correlation is like 70%. So these are some numerical figures for on correlation. So I take positive correlation values which are more than zero point 0.4. So the correlation will be given in will vary between -1 to 1. So I leave out the negative correlation, and I take only positive correlated features, and those positive correlated features should be greater than 0.4. So I print all the positive correlated feature which are correlated with the sale price, which is greater than 0.4. So that shows how strong that relationship is, and this is by the numerical values, and the above heat map is just a visualization of how strong the relationship. So from if you see the overall quality and the sale price, it is like darker blue. That is, we showed like 0.8, 0.79. So which shows the sale price and the overall quality is highly correlated. Meaning, if the sale price is 7, like overall quality is 7, and sale price is $100,000, if the overall quality is less, like 5%, is 5, and the sale price will also decrease very highly. So, and vice versa. When one feature increases, the sale price will also increase. So from this heat map and from these numerical numbers, one or two things we can get up. So people give more judgment to the overall quality rating, and also people give more importance to the garage. People give more importance to garage characteristics, meaning garage cars, number of cars in the garage, and the garage area, and also garage year built. So these three features, garage features, people give more importance. Suppose, let us take one assumption. Suppose you have a, like a house rated like a decent house with a normal area, which is not very big house, like a medium sized house. But garage if you have a garage area and a parking lot, like you can, like garage space of like two cars or three cars, and the garage is newly built, so your house may have a chance of getting highly priced. You can sell your house a little bit higher. There is a chance. So, meaning what it should, the projection it shows is people give more importance to garage and their cars, so that have like positive correlation with the sale price. So these are one or two small inferences you can get from it. So these inferences are useful, meaning in the future, if you wanted to give some advice to some brokers or some buyers, house buyers, you can, or some house sellers, you can give an advice that if you please consider having a small garage or parking lot, so that your price of the house may you can increase it to like 15% or 15%. Like this inferences you can come up. So for these inferences only, like these correlation analysis is like very useful and are like widely used. And so what I have done is, so as of now, we have analyzed until now what are the important features out of 74 features. Uh, we take like consider top 14 or 15 features into consideration, and the top 14 or 15 features we take it, and I take it and be using it. I'll be using to create it as a separate data frame. So So from the original data frame, I'm fetching only the 14 or 15 features. I'm just slicing it and form a new data frame. So now here also there is, we need to make a small changes, because from the previous, if you see the previous header, you can see the year of house, year of built. So the year of built is like 2000, 1976, 2001, 1915. So all these, so uh, year the remodification is done. So which is also done in year, and the garage built is also done in years. So all these values will be in 2000s or 2001, or will be in year. So I've done a small categorical split. So I have considered year which is greater than 2000 is like you can put it in category ones, that is like newly built, like last 15 or 20 years house, like house and garage modifications done between 1950 to 2000, you can bring it as category 2. And the house is like built like all the years which is less than 1950, you can bring it as category 3. So I've done this small numerical modifications, because if you see the entire data sets, all the years will be in 2000s or in 1900. Like these, this will make the data more squeedness. To avoid the squeedness, uh, I have introduced these categories, like a category 1, category 2, category 3. So I'm making this modification. So after I do this modification, so this is the modification in the data set, what I have done it. So now I have done the scatter plot and bubble plot to show how the data, like future insights on data analytics can be done. So these, so like last 10 minutes is left. So I'll directly go into building the machine learning models. So, so those are the features. In this step, I am just trying to identify the outliers in the data set. How do you identify the outliers? Usually, the general procedure, what we do is we try to put a scatter plot. Suppose in the above scatter plot, if you see, like these two top, like is, if you see all these data points are like varies between 100,000 to 600 or 500,000, but only two data points is above 700,000, but which is rated 10. So, but which is like two are separate. So, when machine learning model is trained on these outliers, it will give more importance to this. It will consider this also. So that so that accuracy the training accuracy will be less on these outliers. So it is better to remove these outliers. But in this example, I have not removed it. I just wanted to show how the outliers and importance of outliers. So these two may be possible outliers, and this one may be possible outlier. So now another chance is like how do you identify the outliers is like I just do a distribution plot on the sale price. When I do the distribution plot on the sale price, see if you see the distribution plot, the distribution plot is skewed towards the left hand side of the plot, which means the positive skewness, meaning the kurtosis is extended towards the right end of the distribution chart, meaning there might be a chances of outliers at this end. So if you see the price value, sale price value above 700,000, there is a small pink value which may be a possible chances of outliers. Because of high value of these outliers, the distribution plot is skewed towards the left hand side. So which is a positive, this one is a positive skewness. And another, through the numeric values, how do you identify the outliers is, if you see, if you print the describe of this feature, you see 34,900 is the minimum, and 25% of it is 1,000, like 130,000, and 50% of this is 163,000, and 75% of this is 14,000. So the jump from minimum to 25% is like very high, meaning 100,000 difference. But the jump from 25 to 50,000 is like 40,000 jump high. And the jump from 50,000, 50% to 75% is like another 40 or 50,000. But jump from 75% to the maximum value, if you see, the jump is like 500,000. So that huge jump, that too in one or two data sets, very minimum data sets, is a is a is the point to be noted. So there is a high chances of outliers in this maximum region. So that is what I showed in the distribution plot. If you see the distribution plot, if you see this point above 700,000, there is a high, that is it is a very good chance this is an outlier. So before going into the training machine learning model, it is always better to remove the outliers, but I have not removed it. I wanted to show how it influences the machine learning models. So there are some methods to remove the outliers. So like you need to scale up or scale down the data, like data scaling, feature scaling is needed. So these are some standard methods they use for feature scaling. So actually, since it is a positive skewness, so for a positive skewness, it is always good to use logarithmic function. Logarithmic function will feature, like feature scaling on doing the logarithmic function is very good. Logarithmic function or logarithmic function plus one. So these two functions works very well for positive skewness. So when these some examples on how the positive speed, like how the minimum maximum scalar and how the scalings, like feature scaling is done. So these are like I use minimum maximum scalar and but I use my own feature scaling technique. So I don't use any of these methods shown here. Sometimes mostly I use logarithmic, but for this example I use my own feature scaling technique. So this is I use the training data sets mean and standard deviation to feature scale the entire data sets. So now, so I'll directly jump into doing the machine learning algorithms. Now, I have, now we have a feature scaled data set of training data set. Now, what we have to do is, I have worked on with the support vector regression. I have worked on with the support vector regression, where the support vector regression I'm training on with the scaled data. So when I worked on with the scaled data, so here I just established the model. Now I fit the trained data with the predictor. This Y train predictor is the sale price, and the X train is the 14 features what I have done extracted from the feature selection process. After we done the correlation analysis, we selected 14 features. So those 14 features will be used as a X train, and these are the response variables. So this is the response, and I used predict method to predict the outcome from the testing data sets. So just for an example, I've done this. So now this is the uh, this is the output. This is the output I have got it from. Uh, this is the output of this regression model. What I've received from the predictor values. So this output is the predictors chart that is plotted against the predicted and the actual. So this one is a small visualization chart where this horizontal line, the best fit the SVM has done is the black line on the current data. So what should be the ideal condition is this black line should overlap with the gray line. So that should be the ideal condition. But for any machine learning models, that is like 100% that it cannot learn. But it should be very close to it at least. But for this, I measure the accuracy in terms of R square. R square is 0.683. R square is a measure of accuracy. What I use, I usually there are other metrics which are used. R square is gives how from the R square you can tell how the built model can learn the variable data set. So that is what the measure of R square is. R square is usually between 0 to 1, and the 1 is very good, and the close to 0 is very weak or poor. So this model is like 68%. So now I wanted to show a small comparison between the machine learning model which is trained on the scaled data and unscaled data. So now I've used the same support vector regressor against the unscaled data, meaning not a scaled data. So when I work on with the not scaled data, you could see the result of the predictor against the actual. So it is a complete horizontal. It is a complete horizontal line, meaning it, and the value of R square is also like negative, which is like very poor. So generally building the machine learning models is is up to the machine learning engineer who knows how well the data is ready, how good the data and what data it has. Now, I plan to use gradient boost. So I used XG boost also. So when I used XG boost, it gave a very good predictor results on the scale. I used XG boost on the scaled data. So when I used the XG boost on the scaled data on this data set, you could see the R square value is like 0.859, which is a very high or very good. Uh, and the black line is also very closely matching with the horizontal, with the slanting 45-degree line, uh, gray line. So meaning it is very close. And here also you can spot the outliers, how the effect of outliers is. Suppose now coming to this SPR support vector regressor, you could see this is the outlier. So for the values, it should predict 7. Actually, 7, it is predicting only 1.5 or 1.6 against the predictor and the actual. So meaning this data is completely out of the model data set. So this is a potential threat or outlier which will decrease the accuracy. For example, for the same SVR model, if you remove this data set from the trained data set, when you retrain the same SVR model, this black line will be even more close, and this R square may show like 0.71 or 0.72. So it this outlier will create this type of inaccuracy or like lot of large prediction errors. So it is always good to remove the outliers. So same is the case if I show you in the XG boost, this is the outlier. So this outlier and this outlier both are same. Both these outliers are created from one particular data row, which we need to eliminate. If we remove that data rows from that, this the accuracy of the XG boost can be further improved. Maybe if you remove this outlier, this R square value may go even up to 0.89. It's a high chance. And one more thing is, I just wanted to add this one. I used a basic XG boost. I have not done any hyper parameter optimization. Like a hyper parameter optimization on XG boosts can be done, meaning hyperparameter, all these are parameters, and hyper parameter optimization on gamma values and learning rate and the child rates, and, the base score, like all these, like 4 or 5, and the max delta steps, like these hyperparameter optimizations can be done. If you follow those procedures, you can improve the accuracy of the learning model very high. So after you build the trained model, now you what you have to save that trained model. Suppose if we have most of the viewers would have used MATLAB. So during the MATLAB, what we usually do is like the trained model, uh, will be saving it as a separate net file, and then that net trained model will be using it to give the input and to predict the output. So same way we can also save this trained XG boost model using a method called pickle. Now I use the pickle library to save the trained model. Now I'm saving that the trained model of XG boost. Now my model name is the XG boost model name is model. So this is the my model name for XG boost. So I'm saving the XG boost model name in the as I'm saving it as finalized model.sav. So it will be saved into your local hard disk, so local drive. So where is, like, if you see the name of this you see the name of this is I've saved it as finalized underscore model dot save. So here you can see here see here. So here I am saving it as finalized underscore model dot save. So this will be saved in the local disk. Now this is a trained, this is equivalent to the trained net file in the MATLAB. So this is the trained file. This trained model can be again fetched in, can be deployed into any real-time system. Can use only the data set, testing data set, to give an input and predict it. So I'm just calling that trained. I'm just calling that trained. I'm just loading that trained. Pickled that saved model using the pickle library. Now I load it as a loaded underscore model XGB, and this loaded model XGB, I'm using the testing data sets. Like for example, I have this testing data set. So this is the testing data set. So before using this testing data sets, for this testing data set, I need to predict the values of sale price, having all these features. So like the procedure we followed above, meaning feature scaling, what are the essential features, like 14 features from this testing data sets is taken up. and all these 14 features is given as an input to this trained net, like a trained model, to predict the output. So the output can be saved here. So just to show how the output comes. So this is how the output comes. So since the time is like 1 hour, I need to rush up, still starting from how to load the CSV file till building a model, feature scaling, feature engineering. So I couldn't touch up the entire each and every topics in depth. I'm sorry for that because of the time constraints. So so now this is the entire code what we have to work. So the steps what we have to follow before developing a machine learning model is, we have a data set. We have a data set. First, we need to clean the data set, identify the null values. Data cleaning should be there, and feature scaling, feature engineering. So these procedures are followed, and feature extraction techniques are followed based on the correlation analysis. After feature extraction techniques are done, and the important features are identified, based on the important features, based on those important features, you train the you select the model, you train the machine learning model, and after you train the machine learning model, you save it in your local disk, and it can be deployed at anywhere in the local machine or any servers. So that trained file can be used to predict the of the sale price or outcome based on the inputs. So this is the session overall what I have showed it to you until now. Thanks a lot for listening. Thanks a lot. And over to you, Mr. Neelakandan.
Thank you very much, Dr. Shivasankar, sir. Very good session. And we have the doubt that whether the machine learning, how the machine learning will predict in data sets, whether when you are going to reach the target accuracy level, how to predict that? Any techniques we need to apply that? You said that training data and data set, training data set as well as prediction.
Your question is, I understand, how do you improve the accuracy of the trained model?
Yeah.
Is that your question?
Yes, sir. Yes, sir.
Actually, in today's session, what I've showed, in the end, I told you how to do the hyperparameter optimization. So,
Okay.
for example, in the XGBoost, I showed you there are like different hyperparameters which can be optimized. That is one. But before going into the hyperparameter optimization, the best thing is to clean the data set. So if you have a cleaned and very good data set, meaning what I mean by cleaned data set is, your data sets should not have any outliers, and all the features are well scaled. So features, after following the feature scaling, and the outliers are removed. So when you train the model, it will give a reasonable accuracy. And hyperparameter optimization of the machine learning models will help you to further increase the accuracy of the model at least by 3 to 4%. So I have that experience of doing it, and to further to improve the modeling, like machine learning accuracy of the accuracy of the machine learning model on that particular data set is, if your data set is large data set, you can work on stack modeling of machine learning algorithms, meaning like stacking up 3 or 4 models together. So that will increase the accuracy at least by like 19 to 20%. Meaning this is applicable only when your original machine learning model is showing a very less accurate. So stacking up the already an accurate model is like not relevant. So this stack model of these procedures can be followed in the later stages, but until you, so these are the ways how you can improve the accuracy of the models.
Thank you so much, sir. Thank you so much for joining with us in today's session. So thank you so much, sir.
Right. Thank you. Thank you. Thank you, Neil. See you.
And the next session, uh, I would like to warm welcome Ms. Goushalya ma'am, is a data science practitioner and a certified blockchain expert in Amtech system. So without delay, I hand over the session to Goushalya ma'am. Ma'am, please take over the session.
Thank you so much, sir. Very good morning to all of you. It's a pleasure to connect with all of you on a bright Wednesday morning. First of all, I would like to kind of thank the management of JPR Institute of Technology for this initiative and bringing across all the change makers from the academic forum and enabling them with this online platform um, for on this emerging technologies. So let me quickly share my screen. So can you quickly confirm if you're able to hear me okay?
Yeah, ma'am. That's way.
Great.
Yeah, fine.
All right. So we have a wonderful lineup of speakers, and I'm sure you have had a very good, insightful sessions on the basic of data science, delving into the applications, and also into kind of soiling your hands with respect to certain algorithms and how it is actually done in a kind of a business scenario. So now what I'm going to take you through is with respect to the aspect of how do you identify the research areas in data science. So that is what we're going to discuss for today. And I'll just quickly get into the session. So as you see over here, and we have been the witness of the time, technology which is used with the right strategy, time, and space has changed the world. And the world of data science is no different to that. In fact, every organization, as they're looking at kind of how do you make decisions, data driven decisions, and how do you kind of ensure this aspect of being more with respect to the aspect of going with the what information the data talks through, and all of that has become a lot of emphasis. And today what we are seeing is data science and algorithms have actually transpired as a super valuable tool in kind of organizing this unstructured data, whipping it into shape, looking at what patterns and kind of insights the data is talking about, and also looking at how you can make more informed decisions, right? So that's what this field of data science and the underlying algorithms are kind of playing around. Now, if you're looking at it, but in a way, if you look, maybe little did we know that this algorithms and the field of data science have started to kind of percolate and rule over every aspect of our life. In a way, they actually kind of influence some of the decisions that as we make in our day-to-day life, right? Be it the products to shop online, or be it with respect to what shows to watch, or cases like what ads we see, what news to consume, and also suggestions on social media accounts to follow. So all of these are, this is actually not an exhaustive list, but if you look at this, the allure of dataism and algorithms have some way it has kind of formed the now cliched Silicon Valley motto of making the world a better place. So there's a lot of aspects within this broader tech stream where there is a scope for research. And so before we get into that, let's quickly look into a representation over with respect to the landscape of what we are dealing with from the broader aspect of data science. We understand it's an interdisciplinary kind of a stream, and here you're seeing a two-dimensional representation. On the y-axis, there is a representation of all the problem statements. On the x-axis, we are looking at the different approaches. And the convergence of these two form the technology stream as what we are seeing as solutions out there in the market, right? Be it robotic process automation, natural language processing being used in being classification, or be it with respect to clustering, in some way being also used with respect to chatbot solutions and all of that, right? And if you look at it, yes, this is the domains. Here we are seeing the approaches at the x-axis, but you also see certain color representation, which is nothing but a macro regroup of these approaches grouped together to form symbolic, statistical, and sub-symbolic representations. And then you also see with respect to the lines being coded lines over here, dotted lines over here, and solid lines. Now, if you have to kind of interpret this, it's more with respect to how the convergence looks at and what kind of problem statements are we trying to solve. So that's what it's kind of looking at. Say, for example, if you pick something like the natural language processing, right? So it embodies somewhere between the knowledge-based, probabilistic, and machine learning approaches of problems, and which is more with respect to the domain of perception. So that is what it's kind of right now trying to kind of solve. And as we see, each one of these representations have a depth of exploration that has already been done in the market, but there is a lot of scope with respect to the research aspect of how we need to take it to the next level, or ensure accuracy, or to kind of ensure that it is the data is not the results are not biased and all of it, which we will look into what those specific areas are. But I wanted to kind of put this across, and I've left the references over here as well. And this is predominantly, it was kind of from the strategic consulting company called Axilo, where they have this for one of their product platform. They had kind of grouped this and put across, but this is a very good classic representation of how the problems are being addressed and under what domains they map into. Now, if you kind of move across, we see that there is we understand it's an interdisciplinary kind of stream, but is data science a discipline? To what level is that? Now we see that there are a lot of courses out there. There is a lot of openings that you're seeing this big huge hype about the field of data science, the data scientist kind of roles, and there's a lot of research that is kind of funding around as well now. But is this discipline something as a complete as you're seeing, or is it something as you seeing the evolution that is going around it, or to what level is this particular discipline distinctive from the others? So to understand that more, let's quickly kind of get into look into some of the meta questions which are around this discipline of data science. Okay, so I broadly put across three different questions over here, and let's try to kind of look into them. The first one is, what are the deep driving questions of data science? Like every other field where you're looking at research aspect, right? Like what is the origin of life from the biology standpoint, or what is the kind of origin of universe from the astrophysics standpoint? There is a deep dive question that every field, when we're trying to do a discipline, we in every discipline that we are kind of looking at. Now with data science, what is this deep diving question that we want to kind of address? So when we are looking at picking the research topic, that is something that we need to kind of look into. As we just saw in the previous slide with respect to the combinations or the convergence of different domains, and the approaches have different technology solutions out there in the market. Now addressing this question becomes very critical before we move forward with the aspect of our research. Now, the next question is, what is the role of the domain in the field of data science? Because experts have always argued the uniqueness of data science in a way that it is not just about the methods, it's not just about the accuracy, it's not just about the context or the domain aspect of it. The domain of data being collected and analyzed is also something we need to look into. The domain for which a question has to be answered to be coming from the collectiveness and the analyzing of data is also something that we need to kind of look into. And we have to also look into the aspect of, is the inclusion of domain completely kind of inherent in defining this field? because it is a convergence, right? To what level is this convergence, and to what level is the research that you're picking, research topic that you're picking has a kind of emphasis on, that is something that we need to kind of also consider. Now, in this way, how much of uniqueness is there when you're kind of picking the topics is what it's kind of driving towards. Now, the third thing is what actually makes data science data science. It's an interesting statement, right? Now, is there a problem unique to data science that can be convincingly argued over and would be addressed? And how much to the other constituent disciplines are we kind of looking at, be it with respect to computer science, be it with respect to statistics, and how we need to kind of look at it. So in coming up with the accuracy of that and coming up with more clarity on how we need to proceed forward, these metadata questions are very, very important to kind of before we move into the topics aspect, or the pointers where we need to kind of look into. Now, this based on these meta questions, right? Now, kind of put across a list of 10 different research areas, and this is no way a kind of order of which is on priority, which is not, and all of that. And so this is, and definitely not an exhaustive list, but definitely a starter to kind of look into. So let's kind of have a look into these areas. Now, the first one I've put over here is the scientific understanding of learning, especially the deep learning algorithms. Because if you look at it, as much as we admire the astonishing success of deep learning, we still lack a lot of basic understanding of why deep learning works so well compared to the others. By no means this is to kind of put this little down, but this is to kind of look into how to kind of understand it better so you can come up with even more innovative solutions. So a little more of scientific understanding around that is needed, because everybody who calls themselves data scientist or kind of working towards in that field at this level, this is still an evolutionary kind of, this field is still in evolution, right? So there's not to a depth of knowledge that many have got into, while there are exceptions, while we are also seeing a lot of extreme talent out there, but a deep understanding of this scientific understanding is still something that we are seeing there is a lag, and we do not know how to explain specifically on why a deep learning model produces one result versus another, and how do you kind of ensure this is the approach to go forward with. We also do not understand how robust or fragile they are to kind of perturbation to the input data distribution, and to how to kind of interpret that. So these are some of the aspects where I certainly believe there's a lot of angle for research, and to probably get into the depth of it. And this is predominantly being the experimental field. So there is probably far, and this field of deep learning is probably far ahead of any kind of theoretical understanding as well. So we'll have to understand it even more deeper is what my take is. Now, the second one is with respect to casual reasoning. Any kind of stream with respect to, if you're looking at, say, for example, the machine learning, like the algorithms what Sir was going through in the previous session as well, right? It's a very powerful tool, and it helps you in finding patterns, in examining the correlation, and predominantly whether it's a smaller data set or a huger data set, it gives you some directions. Now, while this adoption of machine learning has opened many fruitful areas in the research, these fields basically require methods which are way beyond the correlation analysis, right? And for that, you need these cases to kind of tackle the casual questions and take it forward. Say, for example, if you're looking at one particular stream, and there is an algorithm that is kind of helping you out in solving that particular problem statement, and you give an explanation, you have a very good explanation of why this algorithm is picked to solve this particular problem versus the other problem, right? So to that level, now we have an advancement. So, but if you're looking at whether how rich and a grown area of this casual reasoning is out there, it is still something that we need to kind of explore more. Now, the other aspect is with respect to precious data. Now, we are talking about data being out there. There is different methods of processing it, handling it, and all of that, right? Now, data can be precious for one of the three reasons. One, it is very expensive to collect. The second one is with respect to it contains rare events. And the third one is with respect to the data set is predominantly kind of artisanal, which is a small or task specific kind of information that it can kind of derive at. Now, while this is there, for each of these kinds of representation, if you're looking, we need new data science methods and algorithms. Right now, we have many of them, but there is also certain things where we haven't been able to kind of handle it in a proper way or not in a convincing way. And that is definitely a scope for a lot of research aspect, because we need these new methods to be in place, new algorithms or improvisations in the algorithm to handle this data sets that we're talking about, and to also consider the domain and the intent of the use of that data that is out there. So this is one angle of aspect of why we need to kind of look into ways of how do you can kind of get that all without taking out all the noises and move forward. Now, the other aspect is with respect to the multiple heterogeneous data sources. So this is not something we are new to it, even from the days of business intelligence and analytics and all these ETL tools. And today we have far more advanced techniques in place to kind of smash all the data together, do wrangling and move forward and stuff. So this is not new, but where the kind of crux is with respect to research aspect is even the state of the art data science method can handle only certain aspects of this heterogeneous sources, or even if they're able to kind of blend everything together, what sensible information can we get out of it is still a question aspect over there. And so what we have to kind of look into is kind of there should be a lot more of focused research in aspects of combining these data sources and provide extraordinary impact. The impact what we have right now, how much of sanity checks are we doing in that? So while we're talking about different kinds of best practices in handling this heterogeneous data, but are they different specific frameworks? Are they different these cloud providers also have these solutions to kind of mash up and move forward, but to what extent the effectiveness is there and how easy is it to do? Because there is always this complaint about 80% of the time is spent in processing, and it's only 20% of the time that we spend in kind of analyzing it, right? Now we are trying to kind of turn this around and kind of ensure that we have enough time, and the business teams are kind of having enough information to kind of move forward. But a kind of an advanced research, a focused research in taking it to a next step apart from whatever is out there right now in the kind of field would probably help a lot. And the fifth one over here is with respect to inferring from noisy and incomplete data. In some way, this is related to the third point of precious data as well. Now, the real world is messy. We cannot have anything in a very kind of structured aspect. And what patterns used to be something that we kind of completely kind of believed into no longer makes sense, especially in a case like what we are right now into, like a global pandemic like COVID, right? So whatever the data was talking about, the trends it was talking about, and all of this has suddenly changed. We live in a completely kind of volatile, uncertain, probably ambiguous kind of environment right now. Now, with all of this messiness, and we often do not have complete information about these data points as well. So yet what data scientists do is they want to build the model from such a data and do the inferences and predictions, and they move forward. And handling this deliberate noise is particularly very important, because we have to kind of add these noises to ensure that we make the data kind of informative at every level of aggregation, and the data has to talk about the current situations that's out there. Now with all of these that's kind of there right now, how do you kind of ensure that we can handle things better, and how do you kind of come up with an ability to better separate this noise from the signal, so you can improve the efficiency and kind of bring in accuracy of these references, right? So in that aspect also we have a lot of scope for research, and that is something that I would probably kind of put an emphasis on as well. So this is one set of aspects on the research area. Now if you're looking at the other ones, this is something that I would probably emphasize little bit more on, right? Now if you have we have already seen rapid development of systems using AI and machine learning in critical domains such as like autonomous vehicles or criminal justice, healthcare, hiring, be it with respect to scrutinizing institute application forms, housing, human resource across different streams, different fields, verticals. We are seeing that algorithmic decision making has become an emphasis, right? And AI agents are directly kind of being deployed and are making an impact in the decisions that we are making. Now consequently there is an increasing concern if these decisions can be trusted to be correct, not just to be accurate on the kind of we're not just talking about the accuracy, but we're also talking about, is it reliable, is it robust, is it safe, is it secure, is it got all the fairness in that under all adversarial kind of attacks like what we have right now as well. Because if the decision, the input, the flow of data that is going to come has bias in that, has noise in that, then the results of it, which is the decision which is made based on this data that is flowing in, will also have the biasness, right? Now how do you kind of segregate these two? How do you kind of put across, draw a line and say that these decisions are completely trustworthy? And at this point it is evolving, but it is not there yet completely. Now we are talking about the continuous feedback loop of improvising the accuracy of the data predictions that we are trying to do, the prescriptions that we are trying to do, and all of it. But how much of trustworthiness does this data even talk to? So that shakes the fundamental there, right? Now if you can interpret the outcome in a meaningful way, and that is one, but how much of reliability and trustworthiness does this bring? So that is something, a very very deep area that we need to kind of research and come back with a lot more of approaches, frameworks and stuff. Now the next one is with respect to kind of putting in, we have all this computing system, from where we began with our initial kind of computational power and all that we had in harnessing the data to where we are right now. I think we have gone leaps and bounds. Now there are novel special purpose processors like GPU, TPU and all of them in large data centers that we are using. But even with all these processing power that we have, and with all the data that we have, with the fastness that it flows, the velocity, variety and all of that that you're talking about, the characteristics of it, right? Basically it's more of the data hungry and the compute hungry algorithms that we are looking at, and there is energy hogs in that. Now how do you kind of ensure that we can kind of rethink the computer designs, system designs from the first principles, with data being the focus apart from the processing of it, right? Now how do you kind of look into this new kind of aspect that we have focused, that we have got into? So that is something that we need to kind of look into. So the new age computing system designs should be considering the heterogeneous processing, effective layout of be it with respect to the massive amount of data that it can process, and also in the pace that it can process the target domain, or be it with respect to the application, the task, the energy efficiency. While this is what all the solution providers from the infrastructure standpoint are claiming to have as their kind of the flagship differentiator between one to the other, but are they looking at it from the data intensive perspective, rather than just from, okay, I can harness, push it, process, I can kind of have these compute storage and network being provided. So as a data science solution, do we have something specific in this to kind of handle it? Now we have also started seeing that providers are bringing up with data as a service for the market to kind of take forward as well. But this is, now we have to kind of, where they are kind of putting in these components in place, but is it something affordable that every data scientist, every business owner can kind of handle it, or if there is, when there is a need, if they can kind of take it forward? That is an area also something that we need to kind of look into, and which needs hardcore research to be focused on. Now, the other aspect is with respect to the kind of automating the front end stages of data life cycle. Now, when we are looking at the data science problems and how do we approach into it, there could be multiple steps. There could be exploratory data analysis processes that we would kind of use and move forward, right? While the experiment is probably the success of it has been more with respect to the methods, the algorithm, the fanciness of it, and all of the aspect of it. It is still a labor intensive and tedious process. And like I said, the kind of preparing and ensuring that it is ready to be kind of analyzed, the focus is spent more of 80% of the time is in processing aspect rather than being kind of analyzing it. Now, in this aspect, if you're looking, this data scientists predominantly, they are drawing on both the computational, the statistical methods, and they kind of devise the automated methods to kind of address these data cleaning, wrangling, and probably without losing the desired properties of the generic ones of accuracy, precision, robustness till the end of the model, right? Now, if you're looking at this, now in the market right now, we have autonomous solutions to even do these steps, like autonomous data preparation, autonomous aspect of kind of analyzing it. We'll come to the analyzing part later on, but at least with the processing aspect, we're talking about autonomous capabilities there. But to what level of autonomous capabilities are they bringing onto the table? On the screen, how much are they able to do? Behind the screens, what is the kind of plumbing that we need to kind of do to kind of handle this scenario? So this is a very emerging work area, and probably that is something that would interest a lot of people as well, with respect to automating the data cleaning process, visualization process, model building process, or model interpretation process. So these are the different aspects in the life science, the life cycle, right? So one stage to the other, and in that, how much of automation can you kind of bring in? And that is also something that needs a lot more of research out there, which is started to kind of get kind of retention. And that's one focus area where products which are providing these tools and techniques are kind of having at this point, but definitely needs a lot more of research to be kind of research time to be put in to bring out certain frameworks to kind of take it to a next level. Now, this fourth point over here with respect to privacy is it interconnected with the first point that we talked about, the trustworthiness of the solutions that we are bringing together, right? Now, today, the more data we have, the better the model we can build. That we understand. But one way to get more data is to definitely share the data streams across the different streams. But we have these regulations in place. We have the privacy concerns. We also need to kind of preserve the confidentiality of the respective parties' data sets. So there's a lot of things that we need to comply towards. Say, for example, the scenario is that if you're building a model to predict whether someone has a disease or not, right? Now, especially like something like the current situation itself, where we are trying to kind of assess if a person is being affected by the COVID or the situations like this, or in future, if you're trying to kind of do this, information has to come when multiple hospitals could share these patient records. We are not able, we can't kind of predict with one or two cases. We have to kind of have these consolidated data to kind of move forward. But we could build a better prediction model only when you have these enough informations in our hand to kind of do that analysis. But in that angle, when we are doing, there's a lot of compliance and regulations that we also have to um, kind of comply towards, right? Like the HIPAA compliance, or be it with respect to the individual countries' compliance policies that we have in the data sharing aspect, and all of these has to be kind of looked into and considered. So we are only now exploring the practical and scalable ways. So as we're looking at scalable data science solutions, these are some things that we will be kind of enforcing ourselves into, kind of putting a checklist on that to move forward. Now, solutions that are out there do have these plugged in, but to what level are they kind of even over the screen kind of handling it efficiently? So there is the industry and the government are exploring methods and concept to kind of look into how you can bring in this secure multi-party kind of computation, or be it with respect to the kind of zero knowledge proofs, or be it with respect to the kind of differential privacy, and all of these points they are kind of putting in now. But this is an area, probably if you're interested in, will have a lot more scope in kind of your research angle. Now, the last one is also tying back to the trustworthiness, what we discussed about, right? Now, the data science solutions, the algorithms that are out there raises new ethical issues. And probably you can frame it in three different axes. One is the ethic of data. The second one is the ethics of algorithm. And the third one is with respect to the ethics of the practices that we follow. Now, when we're talking about data, how the data is generated, recorded, shared. Like I said, if there is going to be bias in the data, your results are going to be biased. But we cannot take biasness out of the equation and move forward, because we know as the society we have biases on different things. So we have to kind of advocate with respect to how do you kind of bring in the bias data in, and after that, when the decisions are made without these biases. But in the algorithms, this should be kind of included to kind of taken, it should be factored in as well. Now, when we're talking about ethics of algorithm, we have to kind of look into how the AI algorithms and robots interpret this data. Are they kind of infused bias in that? So that is also something that we kind of need to look into. Now, with respect to practices, the ethics in the practices, devising of these responsible innovation and professional codes, especially in this emerging field, should have all these criteria for specific set of flow to kind of follow. Right now, do we have that, or are we practicing that? That's a question that we need to kind of deeply kind of ponder upon. But that is, we definitely need to kind of address the questions around the ethics in data, the ethics in algorithm, and the ethics in the practices, to ensure that we have a, when we're talking about a decision, a data driven decision, and here's an algorithm which gives you that angle towards it, it should be something that we can trust and move forward, and not kind of take it in a one sided way, right? So this is what from the last slide, and over here what we have is areas where there is scope for a lot of research that you can kind of put into, and kind of delve into a lot more of intelligent frameworks or wireframes that you can kind of develop. Now now many, of late you're seeing a lot of institution offering data science courses, a lot of kind of certifications on all these are kind of coming up a lot. There is hype, there is a kind of so much of hype towards this discipline, and there is a lot of flocking towards it. But you should also kind of look into the convergence of different streams along with kind of data science. Say, for example, the convergence of blockchain with data science. End of the day, both deal with data, right? Now, if you're talking about data science for prediction and kind of prescriptive, Now, blockchain is about handling it in the data integrity aspect of it. Now, these kind of convergence streams is also something that we can kind of heavily kind of look into the areas of research and do a lot more of aspect as well. So this is still a very evolving stream, and what we have seen right now as we are consuming these solutions, or we are using these solutions in some form or other, is just the tip of the iceberg, and there's a lot more to kind of explore. And across the world there's a lot of kind of research that's going around and taking it to the next level, as every technology has its peak and then it becomes kind of mainstream. Now we are going towards the peak, and we are starting to see that from academic it's getting into mainstream right now. So there's the scope for research is pretty huge, and I would invite all of you to kind of contribute in this space, and kind of, if there is a specific interest that you have and a specific stream where you're already researching, and probably it is the time is now to kind of take it forward and move to a next level and make the differences, as you're already making differences in the academic side, influencing the future leaders. Now this is also something that probably we can kind of look into. So with that said, I leave all the handles over here. So please feel free to share your feedback and your if there is any specific questions, I'll open it up for taking it up. And thank you so much to Devanathan sir and Neelakandan sir for facilitating and hosting this session. Over to you, sir.
Thank you so much, ma'am, for sharing your experience. So actually, we are broadcasting in YouTube only today. I think if there is any doubt, I will give your contact number and mail ID. Definitely, they will contact with you. So thank you so
Sure.
much for joining with us. Thank you, ma'am.
Thank you so much, and all the very best to everyone.
Thank you, ma'am.
Thank you.
Dear participant, and there is an attendance link. Our coordinator will share in Telegram also. So kindly note down. The quiz link will be shared in Telegram. Okay. And this is an attendance link. Quiz link will be shared in Telegram group. And same attendance link also we shared in Telegram group. Kindly record your attendance. Again, I'm repeating, quiz link will be shared in Telegram group. If you don't have roll number, kindly fill the roll number as an JITDS new. If you don't have roll number, kindly fill it JITDS new. This link will be shared in Telegram group.